Here we are. Hypothesis tests. We're doing, in this case, it's going to be called a two-sample t-test. So instead of a two-sample t-interval, today we're looking at a two-sample t-test. We're looking at a hypothesis test. And again, your null hypothesis and alternative is going to be about the mean difference. That the mean difference, null is usually going to be the mean difference is 0, and an alternative, it depends on whether it's one-sided or two-sided and what direction it is. Remember that if it's easier for you, you can also state these as mu1 equals mu2, and then our alternative, mu1 is greater than mu2, mu1 is less than mu2, or mu1 is not equal to mu2. And if that is easier for you to make sure you're stating your null and alternative correctly, then feel free to do it that way. But then your formula should be in terms of the mean difference. Speaking of formulas, there shouldn't be any major surprises in the formula sheet. There shouldn't be any major surprises in the random, normal, and independent conditions. Oops. Once again, statistic minus parameter over standard deviation. So remember, this is what you get in your formula sheet, and you have to put in these pieces. Right? The mean difference of the statistic minus the mean difference of the parameter, which was usually 0, because that's usually our null hypothesis, over standard deviation. We figured out this standard deviation formula yesterday. It's the same one we used in our confidence intervals.
Except this was squared. And in confidence intervals, we don't square it, right?
This had square root of this squared, yes. And we went over how that worked yesterday. So it's basically the same idea. We're using t-scores. If you're doing it more or less by hand and using the table, then the degrees of freedom you're going to use is the smaller of the two sample sizes, just like we did with the confidence intervals. If you're doing it on the calculator, you're going to see that it's actually going to give you a degrees of freedom. And so you would write that down in your step 3 instead of the smaller of the two sample sizes. So it just depends on how you're doing it. Most of you, you're going to write down the degrees of freedom that the calculator tells you. Oh, look, the conditions are random, normal, and independent. Remember, you're checking it for each of the sample sizes. And there's the formulas. And then which tail we want depends on which side of the alternative is. All right, here we go. Again, I'm looking at hitting the main points here. The main ideas. Null and alternative. We want to look at whether this is a one-sided test or a two-sided test. So let's see. Increasing the amount of calcium in our diet. Reduce blood pressure. Okay, so we're looking at whether it reduces blood pressure. So that means that our alternative should be one-sided because we're looking at a change in a particular direction. And let's see, the response variable is the decrease in blood pressure. So how much did it decrease by? So we wanted to reduce the blood pressure. We want it to decrease by more in the calcium group than it does in the placebo group. So in other words, we're looking for, is this mean bigger than this mean? So the alternative is going to be that mu1 is greater than mu2. In other words, that mu1 minus mu2 is greater than 0. So that's your null, that's your alternative. Make sure you define what each of the variables are. Going on in 10 seconds. .05 alpha level. You should have data in list 1 already, or list 1 and list 2. Step 2, this is going to be our conditions. Let me just talk through it, and then I'll show it, and then we'll go on. Random, the big thing here. If you say simple random sample, you are incorrect. There was not a simple random sample here. The part that is random is the assignment to the two groups. The 21 people were randomly assigned to the two treatments. That is what is random about this process. Do not put SRS if it's not an SRS. Normal. Sample sizes are less than 30, so we need to check some plots. Remember that the thing we're looking to be linear is called a normal probability plot. You want to make sure that you're saying the correct thing that you're using. Don't just say the graph. Which graph are you talking about? And then independent, here they just say that the observations are independent. So there is your step 2. 15 seconds. That works too, yes. Any other questions on the conditions?
Does the independent also work for the n multiplied by 10 rule for this one? Or no?
Yeah, that'll be fine.
Okay.
Anything else before we go on step 3?
Can we say, so due to random assignment, these two groups could be viewed as independent? Can that be said for every independent in this unit?
It depends.
Okay.
It depends on, you would have to think about, are these different, are these different observations independent? Does one person's blood pressure affect another? No, then they're independent. That's why they're independent here. All right, moving on to step 3. Remember to write 2-sample t-test in your step 2, the name of the test. Formula, plug in the numbers, answer. And if you're using the table, then we'd use the smaller sample size degrees of freedom of 9, and we get the p-value being somewhere between 0.05 and 0.1. We're going to get a more specific one out of the calculator. So here comes your calculator, where your data is already in list 1 and list 2. Stat tests. Two-sample t-test. That's what this one is called. It matches what you put in. It should match what you put in step 2. Do I have data in my list? Oh, yes, I do. So list 1 is list 1. List 2 is list 2. Frequencies we don't touch. The alternative is that mu1 was greater than mu2. Pooled? No. There's my t-score and p-value. So same t-score. Notice that it gives a degrees of freedom here of 15.59. So in step 3, you would write degrees of freedom equals 15.59 because that's what the calculator is giving you. And if you're using t-scores, you should be putting degrees of freedom. And then give your p-value. P-value is, step 4, p-value is greater than our alpha level. That means we're going to fail to reject, means there is not enough evidence for our alternative. Not enough evidence that it reduces the blood pressure. So let me put that up there for you. There you go. And questions? Two-sample t interval, you would need to get the, you'd be getting a t-score. We got a t-score out of the calculator with inverse t, and we use the smaller sample size degrees of freedom.
Okay, that makes sense.
So for the intervals, you do need to use smaller sample size minus 1 for degrees of freedom. For the hypothesis test, it's going to tell you it's going to give you a degrees of freedom to use, and whatever degrees of freedom you're using to solve the problem is what you should write down. Yes.
For step 2, do we have to find the little charts box plots and stuff?
You should describe them.
So how can we find those on our calculator? That's fine.
Oh, if you need those on your calculator, let me. So. To find these on our calculator, let me turn off some graphs that I was using in AP Calc here. And remember that our menu for all our graphs is second y equals for our stat plot. Want to make sure it's on. Some people go like, it's not showing up, and it's because it's not on yet. So make sure it's on. And then we can have our different lists. Remember that the box plot is here, and then our normal probability plot is here. Those are the two main ones that you would be using. You do not have to draw them on your paper, but you should describe how symmetrical the box plot is and how linear the normal probability plot is. That's what you'd be looking for. I would go Zoom 9 for Zoom stat. There's normal probability plot for list 1. And then you could go back and do the same thing for list 2. Other questions? So, yeah, you can also, real quick, you can also scroll, if you have something in here, this will turn it, so if like I have y equals 2x plus 5, for example. And I'm going to keep that in there, but I don't want it to show up right now.
Scroll over.
This is highlighted so it's on. I hit it again, it turn it off.
Okay, thank you.
And now it won't show up, but it'll still be there for you to use later if you need to. Someone else had their hand up.
So when you're doing it, after you get the whole thing, the t-score equals 1.604, you would write p and then parentheses, so probability that z is greater than 1.604
Yep.
equals, okay.
You would also write whatever degrees of freedom you're using.
Gotcha.
So in the calculator, you would use the degrees of freedom equals the 15.59, I think it was. And then give your p-value. So the things you need to write in step 3 here, formula, plug in the numbers, answer. And then since we're getting a p-value out of with a t-score, we also need to write degrees of freedom, and we need to write our p-value. And then write our step 4 sentence. Very quickly, I'm not even expecting you to write all this down. I just want you to take in this idea as a reminder. If I were to do a confidence interval, here's a 90% confidence interval. Notice what value is in that confidence interval. 0. Remember that a confidence interval tells me about the two-sided test. So if I have a 90% confidence interval, that can tell me information about a two-sided test at a 0.1 alpha level. And it would tell me that we would fail to reject because 0 is a plausible value within that confidence interval. So if it asks you a question like, so that might look like, in a free response, that might look like asking you to make a confidence interval and then asking, based on that confidence interval, what do you conclude about the hypothesis that the mean difference is 0? And then you would say, well, we can link a 90% confidence interval to a two-sided test at a 0.1 alpha level. And that depends on whether our value that we're looking for, in this case 0, is in my interval or not. If 0 weren't in the interval, that would tell me we'd reject at a 0.1 alpha level for the two-sided test. So I just wanted to remind you of that. And then a couple other quick things. This you should already know. Remember, if n is greater than 30, then we don't need to do the box plots and normal probability plots and all that stuff. N is at least 30 means we can use approximately normal and we're done with the normal condition. That's just a reminder of that. And if n is less than 30, then we need to check to see if we would overturn our normal condition. All right, last thing. The two main ones here that I want to make sure that you know, some of these you should already know, like, randomized experiment is good. Here's make sure we have randomization in there. In other words, make sure the random condition is met, all that kind of stuff. The two main ones are this second one. Make sure on these, when it asks pooled, you put no in the calculator. That's big thing number one. Big thing number two, do not use two-sample t procedures on paired data. Remember at the end of the last chapter, we had what was called a paired t-test. And we had that paired t-test where we had those two different samples, and we did list 1 minus list 2 to treat it as one sample, and then just use a t-test for it. So keep an eye on, and there will be some homework problems that have you practice this, whether you're using a two-sample t-test or whether you're using a paired t-test. Remember that you use a paired t-test for a matched pairs design. And so things that you can look for is like, can we treat this as coming from one sample? Well, in these cases, no, because like on that last one, we had our group of 21, and then we split it into two separate samples. So we're going to use a two-sample t-test. An example of when we did a paired t-test was something like we had the same people and we wanted to compare their reading scores, and so we gave them a test before the program and a test after the program, and we're measuring the difference in the two. So we have the difference between the two that we're subtracting, but it's coming all from one sample of the group beforehand and the same group afterwards. That's what lets me pair this bit of data together. I compare these two scores because they come from the same person, just one taken before and one taken after. Over in this example, for instance, we put this data in list 1 and list 2. There's no reason to pair this 7 person with this -1 person, right? There isn't any logical reason to pair those together. So that's what you'd be looking for as to which one to use. Any questions before we wrap up here?
The way I'm going to say this is going to be kind of confusing. The example that you just used,
Yes.
where you take one group of people and you test their before and after, that would be a paired test because you would find the mean difference between their before and after.
Right.
But if you were comparing two separate groups and their before and after, that's what this is. So like
It would be a two-sample there. Yes, you're on the right track.
Okay.
So the question was like, if we had two separate groups and then talked about their before and after, then you would be comparing. What you'd be comparing is the difference between group A that was maybe in program A and group B that was in program B. Then there are two separate samples that we need to think about. If there is some strategy or way that they're clearly being paired, then we can treat it like a one-sample formula and do a paired t-test. If there are two separate samples, two-sample t-test. Again, there'll be some homework problems that will have you practice that. Any other questions? Okay.